Okay, hi guys. We have sound this time, thankfully. So this should be a little bit better for us. In this section 9.2, we're learning about infinite series. Last class we learned about infinite sequences. The only difference between a sequence and a series is a sequence looked something like this, where you were just listing a bunch of numbers, right? The sequence might be 1, actually let's do the 2, 4, 6, 8, 10, right? It's just a list of numbers that are in order, whereas a series is the sum of those terms, right? So the series would be 2 plus 4 plus 6 plus 8 plus 10, right? Plus whatever the nth term is once you get there. And because we're talking about infinite series, we're going to go all the way to infinity, right? We're going to add these up forever and ever and ever and try to figure out, does it add up to a specific number, or does it just keep increasing forever, or does it decrease forever, or does it do some funky something else, right? So that's what we're trying to figure out in this section. The first thing we want to do is get a really good understanding of what a series is. So we're going to talk about convergence and divergence, and one of our first tests we need to talk about partial sums, right? So the main goal here is to add up an infinite amount of terms, but we can't actually do that, so we talk about partial sums, right? Like adding up a few of the terms. So the terms in this that we'd be adding up would be a1 plus a2 plus a3 plus a4 plus, eventually you get to an, and then there's even more beyond that, right? It doesn't ever stop. But the partial sums are S1 is the sum of the first one term, S2 is the sum of the first two terms, S3 is the sum of the first three terms, and Sn would be the sum of the first n terms, whatever you choose n to be, right? Maybe it's like 100. You add up the first 100 terms and you see, if what it looks like. And the idea is, if you look at enough terms, eventually you're going to see like a pattern of like, oh, well, this is approaching 1, right? This sum is, as I add up more and more terms, I can see that the total sum is getting closer and closer to 1, or oh, it's getting closer to 5, or oh, it's just going up without bound and never stops increasing, so it's going to go to infinity. So what we say is, if the partial sum converges, right, if I can see that the sum of these things is converging, then the series is said to converge and has the same sum as whatever these numbers were approaching. Okay, so it's a little bit confusing to think about it without actual numbers. So we'll do an example with numbers so you can see what it actually looks like. So the formal definition is here in this box. So we have this series, right? And then the nth partial sum is given by that same thing we just wrote up there, right? Sn equals a1 plus a2 plus a3 plus blah, 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 blah. And it converges if the sequence of partial sums converges to S being the sum of those partial sums, then the limit is called the sum of the series. The idea is you're going to have, if you do the partial sums, let me just write it down here, you're going to have S1, S2, S3, S4, Sn, right? You're going to have a list of numbers, for the sum of the first term, the sum of the second term, the first two terms, the sum of the first three terms, the sum of the first four terms. You're going to have a sequence of sums, and if the limit of this sequence, right, if the limit as n goes to infinity of that sum, if this sequence is approaching a fixed number, like you just looked at last chapter, if this is equal to some number, sorry, it shouldn't be L, don't give it another name, it's called S. If that equals S, some other fixed number, then that's the sum of this series. Okay, so I know this is confusing. Let's look at an example. Okay, we want to try to find the sum of this infinite series here. first let's talk about what this series represents. What we'd do is we'd start at 1, right? We start here, we'd plug in 1, and we'd get 1/2, right? And then I would add that to the next term in the sequence in the series, which is 1 over, plug in 2 now. 2 to the second is 4. And then I'd add that to 1 over 2 to the third, which is 8. And I'd add that to the next one, which is 1 over 2 to the fourth, 16. And I would just keep adding those up until I get to, well, forever really, because it's an infinite series. So just keep adding them and adding them and adding them. And the question is, does that whole sum approach a fixed number, right? So let's get a sense of this before we do like the, like the real mathematical sense of it. Let's just get a sense of it on our calculator, okay? So let's take 1/2, right, and add that to 1/4. I'm going to start doing this. That gives me 0.75. And then we're going to add that to 1, let's start writing it this way, 2 to the third, that's 8. That's 1 over 8. And then we're going to add that to 1 over 2 to the fourth. Dang it. 1 divided by 2 to the fourth. And then we're going to add that to 1 divided by 2 to the fifth. And we're asking ourselves, is this number that I see there, is it approaching a fixed value, or is it increasing without bound, or is something else happening, right? So I don't know if you can see it yet, but is it? Do you think is it gonna pass 1? I don't know. Let's see. That's 2 to the 8th plus 1 divided by 2 to the 9th. Right, I'm just adding more and more terms up, and you can see that it's getting really close to 1 now, right? 0.998. Do you think it's going to pass 1? You'd have to keep going to actually show that maybe it does or maybe it doesn't. And this is not a real formal way to do it, right? You can kind of see intuitively, like I think it's not going to pass 1. It doesn't, it doesn't look like it's going to pass 1 to me, but I can't be sure of that. So we want a way to do it, mathematically. So that's where these partial sums come into play, right? So let's talk about these partial sums. The first partial sum is simply the sum of the first term, right? The second partial sum is the first term plus the second term. And the third partial sum is the first plus the second plus the third. And the fourth partial sum is, same idea. And, dot, 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 I could keep doing that forever. We want the nth partial sum, right? So like it's really helpful if we can write a explicit formula here that will give me the actual sum. So let's look at these numbers here, right? Let's actually look at what these are. 1/2 is just 1/2, right? So just write 1/2. 1/2 plus 1/4 is 3/4. And 1/2 plus 1/4 plus 1/8 is 7/8. And then 1/2 plus 1/4 plus 1/8 plus 1/16 is 15/16. So what we want to write down here is a formula that will give me these blue numbers here, right? Can I come up with a formula that will give me 1/2 if I plug in 1, 3/4 if I plug in 2, 7/8 if I plug in 3, and so on and so forth. So again, we're going to separate numerator and denominator. The denominator, you notice, is the same as these denominators, right? Which were just created by doing 2 to the n. So the denominator here is just 2 to the n. And then if you notice the numbers on top, 1/2, 3/4, 7/8, 15, 16, they're always 1 less than the denominator. So that's just 2n, and you subtract 1. So this s to the n will tell me the nth partial sum, right? This is the s to the n. And so what I'm interested in is knowing if I go far enough, right? I can't actually go to infinity, but I can approach infinity. If I go far enough, what would the nth sum look like, right? So what's the limit as n goes to infinity of that? And hopefully you can see that this 1 becomes insignificant, and so you basically have 2 to the n over 2 to the n, which cancel each other out, and this approaches, it goes to 1. It's getting really close to 1. It's always a little bit less than 1, but it'll be really, really close to 1 eventually. Right? So because the limit of the nth partial sum converges to 1, we can say that the sum of the infinite series, we can say that the sum of this series is equal to 1. Right? Now there is a more geometric way that helps you understand why, if I add an infinite amount of numbers, do I get 1, right? So I'm going to find some space. I'm just going to go ahead and do it up here because there's some space up here. Here's a square. We can do better than that. And this is 1 square, right? Imagine this is 1 piece of bread or something. What my series here says to do is add half, right? So I'm going to take 1/2 of the whole. There's half. And then I'm going to add 1/4, right? So 1/4 is right there. Add a 1/4. And then I'm going to add 1/8. 1/8 is just half of a 1/4, right? So there's 1/8. Blue. And then I'm going to add 1/16, which 1/16 is, ooh, bad choice of color. 1/16 is half of 1/8. Right, so that would be here, 1/16. And you can imagine keep doing this, right? Now you're going to take 1/32, which is half of 1/16. And you take half of that, and you take half of that, and you take half of that, and you take half of that. And you can see that you're never actually going to go past 1, but you're just getting really, really close to 1. You're getting closer and closer to having the whole as you add each little piece on there. And so this, this little geometric way of looking at it can help you understand why, if you add up a bunch of numbers, you get 1. All right, so that's that for that one. The idea is you write the partial sums out. You try to find an explicit formula for the sequence of partial sums, and then you find the limit of that sequence as n goes to infinity. The 2 main questions you're going to be asked is, does a series converge or diverge? Diverge would be like that sum goes to infinity. And it's kind of nice when they diverge because you're done. If the series converges, what is the sum? So that's the trick, is you got to find out like what does it converge to? All right, so let's do this next example. We're going to go ahead and just start with our partial sums, right? We're going to find the first partial sum, which means you plug in 1, and you just write the first term, right? So this is going to be 1/2 minus, no, sorry, I'm jumping ahead. If I plug in 1, I get 1 minus 1/2. If I plug in 2, I get 1/2. No. S2 is the sum of the first 2 terms, right? So the S2 is the first term, which is 1 minus 1/2, plus the second term, which is 1/2 minus 1/3. And then S3 is the sum of the first 3 terms, which is the next term here is 1/3 minus 1/4. And let me see if I can like copy or something, because it kind of gets annoying to just keep having to do it over and over again, right? So if I can just copy this, nope, that's not gonna let me do that. Anyway, you can see how like you could just copy these things, and our goal here is to figure out Sn, right? Is there a formula I can figure out for Sn? I don't have enough written here to figure that out yet, because I actually need to write out like what is this sum, right? So if I want to write some numbers, this first one is 1 minus 1/2, which is 1/2. The second one is, this first thing I know already is 1/2, so it's 1/2 plus this red piece, which 1/2 minus 1/3 is 1/6. So it's 1/2 plus 1/6, which is 4/6 or 2/3, right? Do this math for yourself. Don't just copy down what I'm saying. Like, actually add these and confirm for yourself that it is 2/3. And then the next one is, these two are 2/3, right? We already did that addition. 2/3 plus 1/3 minus 1/4 is 1/12. So 2/3 plus 1/12 is basically 2/3 is 8/12. So 8/12 plus 1/12 is 9/12, which simplifies to 3/4. And so what we're trying to do is figure out a nth term, right? Can I write a formula that will give me 1/2, 2/3, 3/4, like 1/2 when I plug in 1, and so on and so forth. Okay, so again, it's easy if you look at numerator, denominator. The numerator, notice, is always the same as like 1, okay, come on, 1, 1, 2, 2, 3, 3, right? So the numerator is always just the same as the index value, so it's always n. And the denominator is always 1 more than that, which is n plus 1, right? And so this is the thing, this is the nth partial sum, right? The formula for the nth partial sum. So what we need to do is figure out, well, what's the limit? Let's go up here. What's the limit as n goes to infinity of n over n plus 1? And you can see that using, you can, in behavior model, you can basically just look at these two. This is going to go to 1. And so since the limit of the nth partial sum goes to 1, this whole series goes to 1, right? The sum of the infinite series is 1. And so again, this series converges. So we'd say converges to 1. All right, there is something interesting about this series that I want to talk about because it's going to come in this, and you can kind of see it down here, this telescoping example. Notice something for me, how there's a negative 1/2 here, and there's a positive 1/2 here. And that continues here. If I wrote a bunch of these, negative 1/2, positive 1/2, negative 1/3, positive 1/3, and this would keep happening. All those middle terms are going to cancel out, right? And all you're going to be left with is 1, and then your last piece, which comes from this negative 1 over n plus 1. So another way we could have written this, it's called a telescoping form, is this 1, right, which came from this first term, minus your last term, which comes from the last piece of this formula here, which is 1 over n plus 1. And this is actually the same formula. Like, prove it for yourself if you find a common denominator, right? You'd multiply top and bottom here by n plus 1, and you would have n plus 1 minus 1 over n plus 1, and then these guys cancel, and you're left with n over n plus 1, which is what we figured out over here anyway. But it's kind of like an interesting way to do it, noticing how these like middle things cancel out because you always have the same term and then like a positive and negative. So it's called telescoping form for that. Okay, so that's just kind of intro to what we're going to do down there in a little bit. But before we do that, let's go ahead and look at this next piece, which is this series here. This series n equals 1 to infinity, the sum of 1. So let's do this. Let's do S1 is 1, right? The first term is 1. S2 is the first term plus the second term, 1 plus 1. And the third term is 1 plus 1 plus 1, right? And so on and so forth. Let me erase this so it's not in our way. This might be pretty intuitive, but can you imagine if you add up an infinite amount of 1s, what are you going to get? It's just going to keep getting bigger and bigger and bigger, right? So you should see it goes to infinity. But if you wanted to, you could, follow the same thought process and just ask yourself, what's a formula that I could get? So I get 1 when I plug in 1, 2 when I plug in 2, 3 when I plug in 3. Well, it's just n, right? And then we're taking the limit as n goes to infinity of n. And you can basically just do direct substitution. It's going to go to infinity. And so because the limit of the nth partial sum goes to infinity, we would say that this series diverges. Right? It's not going to approach a fixed number. It's going to go to infinity. Okay, let's talk about, again, this telescoping form here, just because it comes up and you want to be able to recognize these when they come up, and it helps you rewrite the series sometimes in order write the explicit formula for it. Okay, you know what? I'm just looking at the standards in this telescoping form. It might not be the most important thing. So what I'm going to do is I'm going to come back to this telescoping form. It requires some partial fractions, and so I'll come back to it at the end, and if you want to skip it, you can. But if you're really into it, you can come back and watch it. Okay, so but we're going to go to move on to something that's way more important as far as what you're going to be tested on, which is geometric series. Okay, this is something that I hope you saw in Algebra 2 as far as series, or maybe calculus, pre-calculus. A geometric series has this form. It basically looks like an exponential function, right? There's some constant here. And then r is some number, and n is your variable, right? So r could be any number, 1, 2, 3, 4, a fraction or a decimal or anything like that, right? But the idea is you can see it as an exponential function, right? There's a constant times an exponential function. And it's really easy to determine the convergence of a geometric series, right? So if you can recognize it as a geometric series, then you can find its convergence and divergence really easily, and you can also find its sum really easily, right? So geometric series with ratio r, right? That number inside there that has the exponent on it is called r. It's going to diverge if the absolute value of r is greater than 1, right? So if you see 1.1, 1.2, 1.3, or the number 5, 6, 7, or even -5, -6, -7, any absolute value of r greater than or equal to 1, then it's going to diverge. But if the absolute value of r is between 0 and 1, meaning like 0.5, 0.6, or -0.5, -0.6, then this series converges, and it has the sum here, a over 1 minus r, where r is that ratio and a is that number in the front. All right, so like you like these ones. If you see these ones, it's gonna, and you can recognize it for what it is, and you can remember the formula, then your life's gonna be a lot easier on this. Okay, so the first thing we need to do is start some examples here. Determine if each series is geometric. If it is, determine if it converges or diverges. If the series converges, determine the sum of the series. So the first thing I want to look at is it geometric? Can I write it in this form, a times r to the n? If you look at this directly, this first one, it is not in that form. It's basically, this is a over r to the n, a divided by r to the n. This says nothing about that. It says nothing about division. But you can rewrite it like this. You can write it as 3 times 1 over 2 to the n, which still doesn't quite help because we want that n over the whole thing. So you could rewrite it again as, right, this is properties of exponents. If I do 1 to the n, that's still just 1, and then that would be over 2 to the n. So it's an equivalent form. And then what you can see is that it is a geometric sequence, right? This is a, and this is r. So it is a geometric series. Does it converge or diverge? Well, what is r? R is 1/2, right? So is 1/2 greater than or equal to 1, or is 1/2 between 0 and 1? Well, 1/2 is between 0 or 1. So we could say since 0 and that 1/2 is r, this series converges. The geometric series converges. Now we need to figure out, since it does converge, what does it converge to? And it's not that easy. It's going to converge to a divided by 1 minus r. So it's going to converge to a, which is 3, over 1 minus r. R is 1/2. Right? You could probably leave that in the AP example. It's going to clean it up. 1 minus 1/2 is 1/2. 3 divided by 1/2 is 6. So it's going to converge to 6. And, this whole thing is actually our answer, right? So that one was geometric and it converges. Let's look at the next one. Is this geometric? There is no a value written here, but you could write a 1 there if you want. So, there's a and there's r. So yes, it is geometric. Yes, it's geometric. Does it converge? We're looking at the r, the 3/2. Is 3/2 greater than 1, or is 3/2 between 0 and 1? So it turns out that 3/2 is greater than 1, so the series diverges. Again, it's nice when they diverge because all you got to do is say diverge. All right. Next one is this series here. Again, we're looking for the format of a times r to the n, where n is, the variable, and a and r are constant numbers, are numbers, right? So we're looking at this, and this, you could rework this however you want. Like we could write this as n squared over 9 and realize that, sure, it has an exponent here, but the exponent's not a variable. This does not look like an exponential function. Therefore, this is not geometric, right? This is not a geometric series. Therefore, we're kind of done because it said if it is, go on. But you could even determine if this converges or not. Adding up these things, it is going to diverge. So let's not worry about that right now. But it's not geometric, so we're just going to stop there. All right. So that's that. Let's keep going on to the last little piece we have to do. It's the nth term test for divergence. Basically, it's just going to give us a quick test, and it's a very helpful thing that you can do real quick just to see if it works. Then it diverges, and you can just say diverges, right? So maybe on a multiple choice test, you just do it real quick, and if it diverges, then you can choose diverge. If it doesn't, then you have to do a bunch of other stuff. But there's this theorem that says if the series converges, then the limit of the nth term is 0, meaning that if you just looked at the sequence of numbers and not the sum, if you just looked at the sequence, then the nth term would be approaching 0, right? So that makes sense because, if I was adding a bunch of numbers together, like 1 plus different things, but let's imagine I was adding 1 plus 0.9 plus 0.99 plus 0.999. Notice these numbers aren't going to 0, right? This number's not getting closer to 0. So basically what I'm doing is adding 1 plus something that's close to 1 plus something that's even closer to 1 plus something that's even closer to 1, and it's just going to keep going to infinity. So the only way it's not going to go to infinity is if eventually you start adding something really close to 0, like 1 plus 0.1 plus 0.01 plus 0.001, right? You're adding something that this is going to 0. So the idea here is if it converges, then that nth term must be getting close to 0, right? But we're not going to really look at that because that's just like that assumes we already know it converges. We're going to do what we call the contrapositive, which says that if the nth term does not approach 0, the limit of the nth term does not approach 0, then this series diverges, right? So if the second thing is false, if this is false, then this diverges. So just a quick test, what does the nth term look like? Does it go to 0? If not, then diverges. Okay, so let's do some examples. This is an, right? This is the explicit formula for the nth term. We just want to know what is the limit as n goes to infinity of this. If this doesn't go to 0, if it goes to 0, then we have to it doesn't mean it converges for sure, but it means we have to test other things. But we can show right here that this goes to infinity, right? It does not equal 0. In other words, does not equal 0. Therefore, because the limit does not equal 0, this series diverges. Okay, another example. Here's my an. Just a quick test. Does the limit as n approach infinity of this, does it equal 0? So again, it's a question of size. Which one grows faster, n factorial or 2n factorial? Well, 2n factorial grows faster, twice as fast actually. So it's going to be something like small over big, which means this limit goes to 0, which means we don't know, if it diverges. It doesn't mean that for sure it converges, right? Just because this limit is 0 does not mean that it for sure converges. All that we know right now is that it failed this test, right? So all we know is that it fails the test. And we would have to check some other methods to figure out what it does. So we'll do. Oh, sorry guys, I blew this one. Hopefully you caught me in there and were like, "Hey, Mr. Stevenson, don't be a Dumbo." So let's go back real quick because this is a pretty basic thing actually. But I was saying that this grows twice as fast. That's not actually true. It is kind of true, but these two things grow at the same speed, right? So we can use our end behavior model basically and say that those like cancel out. So we're left with this, which approaches 1/2. So the limit as n goes infinity of the nth term is 1/2, which is not 0, right? Therefore, we can say it diverges. My apologies. That was a big mistake. Let's look at the next one. And this is the one we want to look at, where what's the limit of a sub n, right? That's a sub n. This one's pretty easy to see, that 1 over infinity, like as n gets bigger here, it's going to approach 0. So because it equals 0, this test fails, right? And we'd have to check other methods to see if it converges or diverges. It doesn't apply. And we haven't learned the specific test for this type of series yet. So for right now, I can just say the test fails and move on. All right, so your homework for this is written on your paper. Let me find it real quick. Okay, so here it is. I just pasted it on here. This is your homework. Please ask lots of questions in class. Talk to each other. Make sure we're getting it as we go. Like I promised, I'm going to go back up to that one telescoping series thing and do it. If at this point you just want to start working on homework, go for it, and that's fine. So I'm going to come back up here and do this one for you because I said I would. So telescoping form, what we need to do here is rewrite this in a way that we can see that it's telescoping. And what that was, if you remember up here, is that some of these terms on the inside, one will be positive, one will be negative, and they'll cancel out. We want to be able to see that when we do this. So what we need to do is actually rewrite this as 2 over, this is a difference of squares, so it's really 2n plus 1 and 2n minus 1. And we're going to basically do partial decomposition to fractions to write it as 2 separate fractions. That's our goal here. So what we're doing is we're saying, well, this is going to equal some number a over this denominator plus some number b over this denominator. This is partial decomposition of fractions. And then try to figure out what the a and b are so that when we find this common denominator, we get that. So the basics for partial fractions is I'm going to take this denominator, multiply it top and bottom to this one, and I'm going to take this denominator, multiply it top and bottom to this one. And if we do that, we're going to get 2an minus a plus all over basically 2n plus 1, 2n minus 1, plus multiply these together, you get 2bn plus b, and then rearrange this a little bit so that you can see that what this has to equal is the numerator has to equal 2, and then the denominators are already equal. And it might help you to write like 0n plus 2. So like for the nth term, the coefficient is 0, and then there's this 2 term here, right? So we're looking at these, and there's an nth term, and there's a term without n. And so you could rewrite these as 2an plus, let me move over, 2bn, and then this term is just those other two pieces, and it's still all over 2n plus 1, 2n minus 1. But basically what we're showing here, we can factor this out to get 2n times a plus b minus a plus b. And so this is the coefficient of the n term, which means I need to make this a plus b needs to equal 0. And then when I do negative a plus b, I need to get 2. So we can set up like a system of equations. We say a plus b equals 0, and negative a plus b equals 2. You can solve this by elimination. Just add down. You're going to get 2b equals 2. Therefore, b is 1. Right? B is 1. If b is 1, then a is negative 1. Right? So all of this, the book just basically skipped all of that and went straight to this other thing, which all of this basically just shows that this piece right here can be rewritten as b is 1, so it's going to be, and a is negative 1, so it can be written as negative 1 over 2n plus 1 plus b is 1 over 2n minus 1. And this is from 0 to infinity. Notice all I did was replace a and b in this to get this guy over here. So that like, again, the book just skipped over everything besides that. So I'm going to go and erase this so I have some more space. And now we can do what we want to do for the rest of it here. So that's a dumb way to erase. All right, so now our goal here is to rewrite it as a telescoping series. So let's go and write some of the sequences, the terms in this, right? Let's go and write S n, just so we can see it. So S1 would be plugging in 1, which is going to give us negative 1 over three plus 1 over 1. This is A1, and then we're going to add the next term, which is plugging in 2. If I plug in 2, I get negative 1 over 5 plus, plug in 2 there, I get 1/3. And then the next term would be plug in 3. That's going to give us negative 1 over 6, 7 plus 1/5 plus, this keeps going on, right? But what you hopefully notice is that there's a negative 1/3 and a positive 1/3. There's a negative 1/5 and a positive 1/5. And all of those are going to keep canceling each other out. And the only thing that's going to remain is this 1 and the very last term that gives me this, right? So the 1 is there, and you have to think like, well, what gave me this, right? What gave me negative 1/7? Well, it was this one, right? So the very last term is that one. So basically what a formula for the nth partial sum would be that 1, and then this guy, so minus 1 over 2n plus 1. And this is the formula for the nth partial sum. And then once you have that, you can determine if it converges or diverges by finding the limit. The limit as n goes to infinity of this, right? And what you can see is that the limit of 1 is just 1, and the limit of this, because the n is on the bottom, is going to be 1 over infinity. Okay, 1 over infinity is 0, and so it converges to 1. And that's a big headache, I know, but at least we got there. All right.